See, analyze the portal frame loaded as shown by moment distribution method and draw the bending moment diagram. Okay. So in the previous class, you solved the two bay, means there were horizontally two frames were there. So there was called two bay single story, but now it is a single bay two story building. This is called a single bay. That is one bay only. This is one story and this is another story. This is called a single bay two story portal frame. Okay. Now, so the properties of this frame are given. This is columns are 4 meter each, beams are 6 meter each. This top beam is carrying 10 kilonewton per meter and this intermediate beam is carrying 16 kilonewton per meter. Whereas the I for these two beams is 3I. Okay. Then now you need to analyze this by what is this moment distribution method. Okay. Now, if you first step as usual calculation of fixed end moments, there are two spans loaded here, that is CD and BE. So you need to calculate the fixed end moments for both the spans, that is CD and BE. First, if you take this BE, it is MFB is minus WL square by 12. So 16 is W, L is 6. Then if you simplify this, you are going to get here minus 48 kilonewton meter. Similarly, MFEP will be plus 48 kilonewton meter. Then coming to this span, it is WL square by 12 again because it is also UDL and symmetrically. So W is 10, 6 is span. So if you simplify, you will be getting here minus 30 kilonewton meter and MFDC is plus 30 kilonewton meter. Okay. Here, one thing is mistake. This columns have 2I. I have not marked that. Column has got beams as 3I, 3I, whereas I for the both the columns is 2I. That in the problem it is given, but I have not typed it. So let me do that accordingly. Okay. Now, joint B, if you take, see again here, first what you need to look at is it symmetric or not first? Is it symmetric? Okay. Anybody?
Yes,
okay, it is symmetric. So you put the one symmetric line, axis of symmetry we will put here. This axis of symmetry is cutting the CD and BE member into two parts. Okay. So whenever you take the K of CD, you should take half of the actual member. Similarly, K of BE will be half of the actual member. Okay, I'll come to this joint B now first. Now I am considering only left part of this axis. So to the left of the axis of symmetry, there are two intermediate joints. One is called C, another is called B. Now, if you take this B, there are three members starting from B, BA, BC, then of course BE you can write, or BE dash also, nothing wrong in that if you write. But what is BA now? It is I by L because far end is fixed. But I, as I told, it is given but not typed properly. It is I of the BA is 2I, L is 4. So if you simplify this, you will be getting 0.5I. Similarly, BC, that is also 2I. I is 2I, so it is 2I by 4. It will be 0.5I. When you come to BE, now what should be the K of BE now? Half of the full member. Okay. That is why I said one, because that axis of symmetry is cutting the member into two parts. So therefore 1 by 2 into I is 3I. The beam has got 3I. So it is 3I, span is 6. 3I by 6. So if you simplify this, you will be getting 0.25I. And if you add all three K's, it gives you sigma K, that is 1.25I. Then K of BA divided by sigma K gives this value, that is 0.4. K of BC divided by sigma K gives you this one. Then K of BE divided by this sigma K gives you 0.2. Again, if you check here, the sum of these three will be 1. Okay. Similarly, now let us go to this joint. One member is CB, another is CD. CB, it is I by L, but I is 2I. Okay. That is 2I by 4. And if you simplify that, it will be 0.5I. What about CD now? How to take the CD, K of CD? Hello? Are you hearing me? Hello? Hello? Hello.
Yes, sir.
Ah,
Yes, sir.
yes, you are listening. Okay. Then what is K of CD? What is K of CD?
Half of I by L.
Yes, half of I by L of that CD member. Okay. So it is I is 3I, L is 6. So if you simplify this, you are going to get here 0.25I. Then you take the sum of these two, it will be 0.75I. Then 0.5I divided by 0.75I, it comes 0.67. Then CD 0.25I divided by 0.75I comes 0.33. Okay. Not animated because already this is a repetitive step. Okay. Now let me go to the moment distribution table again. So what is this? First you need to write joint members distribution factor fixed and moments. So if you go to the A joint, there is only one member AB. If you go to B joint, it will be BA, BC, and BE dash I have written because half member we are considering. Similarly, CB, and CD dash because we are considering only left part of the this one. A now. AB, BA, BC. This half means BE dash I have taken. CB, CD dash. Okay. Now, once if you write this joints and members, enter the distribution factors of the corresponding member. So BA, BC I have added, BE dash is also added, CB is 0.67, C dash is C D dash is 0.333. Okay. Now enter the fixed and moments. So okay, AB is not carrying any load, so AB and BA will be 0. Similarly, BC is a column that is also not carrying any load, fixed and moment is 0. BE dash is minus 48. Actually, EB will be plus 48, but EB is not coming here because it comes in the other half. So it is to be minus 48. Then C joint, CB, it is a column again, no moment because no column is carrying load here. But CD dash is minus 30. But DC is, it is coming in the other half. I am not taking that. So while entering this fixed end moments, you should be very careful. That's again, I am repeating that word. So once if you enter the fixed end moments, the usual process is balancing and carry over. Okay. First, you need to balance joint B. So it is a 0, 0, minus 48. It means minus 48 is the unbalanced moment. So balancing moment will be plus 48. Plus 48 into 0.4, you will get here 19.2. Plus 48 into 0.4, again it is 19.2. Plus 48 into 0.2, you will get here 9.6. Coming to this joint, 0 and minus 30. So unbalanced moment is minus 30. So balancing moment will be plus 30. Plus 30 into 0.67, you will get here 20.1. Plus 30 into 0.33, you will get here plus 9.9. This is the balancing step. Next, you need to carry over. Let us come to this first. BA, it will be carried out to AB. Half of this, 19.2 divided by 2 is 9.6. Then BC, where it should go to CB. BC to, look at this, BC will come here, CB, half of this is 9.6. BE dash or BE, it will go to EB, isn't it? But EB is not there in our list because we are using the symmetric property. That is a shortcut method we are using. So that is not going to carry. Next, CB, where it should go to BC. BC is there in our list. So it will 20.1, half of that will be 10.05. Now CD, actually it has to go to DC, but DC is not in our list because it comes in the other half because we are using the property of symmetry. Okay, this is how the first cycle completes. So next balancing, again now 10.05 is the unbalanced moment. So minus 10.05 into 0.4 will be minus 4.02. This also minus 4.02 because the distribution factors are same. Then 10.05 into 0.2 gives you minus 2.01. Coming to this joint, 9.6 is unbalanced moment. Balancing moment will be minus 9.6. Minus 9.6 into 0.67. It comes minus 6.432. Similarly, minus 9.6 into 0.33 comes minus 3.168. Then carry over. This to this, it will be minus 2.01. BC to CB, it will be minus 2.01. BE to EB, no EB is there. CB to BC, it comes here, minus 3.126. It is a half of this one. Then again, this CD goes to DC, but no DC is there, so it ends. Similarly, if you again come to this, now unbalanced moment for this is 0, this is minus 3.216, this is 0. So plus 3.216 will be the balancing moment. Plus 3.216 into 0.4, it comes 1.286. Plus 3.216 into 0.4, this comes again. Plus 3.216 into 0.2, it will be coming 0.643. Similarly, this is a plus 2.101 into 0.67, it comes 1.347. Plus 2.01 into 0.33, you will be getting 0.663. If you carry over, this will be 0.643, this will be 0.643, this will be coming 673, and this is not carrying over, this is not carrying over because those ends are not here. Next, balancing. This is unbalanced. Minus 0.673 will be balancing, multiplied by 0.4 comes here, multiplied by 0.4 comes here, then multiplied by 0.2, this is minus 0.135. So this is 0.643. So balancing moment will be minus 0.643 into 0.67 comes here, minus 0.643 into 0.33 comes here. Carry out this distribution. Okay. So same thing, you need to continue this last cycle. So you know that last cycle ends with balancing and carry over to the extreme end. Here only one extreme end comes because I am taking 50%. So if you do this and if you sum up, you will be getting 8.141. If you add from here 16.283, this is 23.574, this is 39.85. You have to see that the sum of these three should be 0. This plus this algebraic sum must be 0. You are getting that. Similarly, CB and CD should be equal and opposite. You are getting 22.772 plus for CB, and for CD you will be getting a minus 22.773. I think this is already done, so I have not animated much for this one. So next, yeah, this is the practical problem here. This is analyze the box culvert shown in figure. So you might have found some nalas and streams where water is flowing. Just there will be a small bridge they are constructing with pipes inside. Have you seen that? Yes, anybody? Those are called as pipe culverts. Have you seen some small nalas? Yes, anybody? Hello? During crossing the nalas road, there will be above road and below there is water passage. Water will flow through some pipes. Have you seen that? Anybody?
Yes, sir.
Those are called as pipe culverts. Okay. Now, if it is small, a bit small, bigger one, they will make some box culvert. They will RCC box. They will prepare, and water over that there will be a bridge-like structure. You throw this box, water flows. Have you seen this? Box culverts, some 2 spans, 3 spans, it will be there. One box culvert I have taken here to analyze. Have you seen such kind of structures? Instead of pipe, somewhat where there is a bigger stream is there, they will put some boxes, RCC boxes. Have you seen it?
No, sir.
No. It is a common structures. You have to observe the structures in and around whenever you are moving, traveling, then you will understand. Instead of pipe, right now, instead of pipe, it is a box of RCC. You assume this much. Okay. Through this box, there is a cross section. Okay. Now, here is a one point load he has given on the top of the box, 12 kilonewton, spaced at the center. Say this UDL is reverse here upward. Why? Means there is a earth pressure coming from the bottom. Pressure is on the base of the box. Therefore, it is up. If the loading is downward, whereas here the pressure is from earth, bottom. So the pressure is towards the base. So this he has given 2 kilonewton per meter. Similarly, this is side earth pressure because there will be earth from the sides. Earth pressure always it goes on increasing towards the bottom. At the top it will be always 0. So it is like a triangular load. So this intensity is also he has given 2 kilonewton. This is common. This and this height 2 kilonewton per meter on this. This is the loading on the box. Okay. Instead of pipe, you are putting here a box of RCC. Okay. Now, is this symmetric or unsymmetric? Yes, anybody? Is this box culvert symmetric or unsymmetric? Hello?
Symmetric, sir.
Symmetric, fine, very good. The axis of symmetry where it comes along this 12 kilonewton, because 12 kilonewton is acting at the center. Okay. Let's look at first. Let me calculate the fixed end moments first. Now, if you take the member AB, so this MF AB will be anti-clockwise. So it is minus WL square by 20. Look at this triangular loading. So if you simplify this by putting the value of W and L, you will be getting minus 1.6. Then MF BA will be, it is clockwise, so it is plus WL square by 30. 0 and 30, this ordinate where it is there, it will be 20. That you have to be careful. Substitute the value of W and L, you will be getting plus 1.07. Now, next span BC. This is the BC span. Okay. It is load is at the center. So what will be the fixed end moment? Minus WL by 8, 12 into 6 by 8, 9. Similarly, MFCB will be plus WL by 8, it will be plus 9. Next, one more span is there, that is CD. This span I will not keep because I am considering only 50% because of symmetry. So MF CD, thus just now I have calculated, but even if you leave it, it will okay. But span PD you need to calculate. What is span AD? See, if the UDL is there, left span is minus, then the loading is downward. But now loading is upward. So this moment will be opposing this action. This is downward. So this will be opposing it. Means it will be first end will get clockwise here. So MF AV is plus WL square by 12. Isn't it? So it will be plus 6 kilonewton meter you will get. Other end automatically it will be minus, it is minus 6 kilonewton meter. Is it clear now at MF AD sign convention? When the downward loading is there, left end will be minus, right end will be plus. But it is now upward loading. So automatically sign convention will get reversed. Okay, is this understood? Hello? Hello?
Yes, sir.
Okay. Now we'll go to the distribution factors. I consider 50%, this side, left side of this axis of symmetry. First you put the axis of symmetry, means how many intermediate joints are coming to the left of axis of symmetry? Here no end joint is there, only it is a closed structure. Previously there was open structure. Now this is closed box. So how many intermediate joints are there to the left of the axis of symmetry? 2, fine. One is A, another is B, fine. I will take joint A. The members coming from A are AD and AB. Okay. What is the K of AB? Don't look at this. Just you tell me. What is the K of AD? You can write AD dash or AD. Nothing will wrong. Yes. Anybody? What is the K of AD? Hello. Why all of you are dull? Looking very dull today. No answers. AD. What is K of AD? Look at the figure. Hello.
Half of I by L.
Yeah, half of I by L. Fine. Half of I by L. I is I only. Here, EI is if he has not given any value of E and I separately, you have to assume that they are I only. Okay. It is I, span of AD is 6 meter because this is 3 plus this is 3. 6. Okay. You will get 0.083. Next. AB. This is a full member now. So it is I by L. L is 4. So you will be getting 0.25. Add these two, you will get 0.331. Right? Next, if you simplify this K of AD divided by sigma K, you will get 0.25. K of AB divided by this, you will get 0.75. Similarly, go to B joint. Right? How many members are starting from B? BA, BC. Okay, BA, BC. BA is full member, so it is I by 4, I by L. What about BC? Hello. What about BC?
Half of I by L.
Half of I by L. Fine. Fine. So it will be again half L is 6, so it will be 0.083. And again, if you calculate this divided by this, you will get this. And the K of BC divided by sigma K gives you the distribution factor of BC. Yes, is there any confusion in calculating distribution factors? If you are getting confused, please ask me. Hello?
No, sir.
Okay. Anybody else? Others are perfectly understood. Okay. No. Fine. Now let us go to the moment distribution method. So as there are two joints, A members are AD and AB, B joint BA and BC. Okay. Let me enter the fixed and moments, distribution factors as already you have calculated. Then fixed and moments, you enter properly. AD, it is plus 6, AB minus 1.6, BA plus 1.07, BC minus 0.9. You have to be very careful. You go through the previous step, keep the values and corresponding values has to be placed. Next, once if you enter the fixed and moments, the process repeats, that is balancing carryover. Now, if you want to balance this plus 6.6 minus 1.6, how much? Can you do it? Quickly, 1 minute. Plus 6 minus 1.6.
Plus 4.4, sir.
Yeah, it will be plus 4.4. So minus 4.4 will be the balancing moment. Okay. Minus 4.4 into 0.25.
Minus 1.1.
Minus 1.1. Similarly, minus 4.4 into 0.75.
Minus 3.3.
Minus 3.3. That is what I have put here. Come to this joint. B joint. Plus 1.07 minus 9. So what is the unbalanced moment?
Minus 7.93.
Minus 7.93. Fine. So it should be plus balancing moment. Plus 7.93 into 0.75.
Minus
5.94.
5.94.
5.94.
Plus, it is not minus because balancing moment is plus. Okay. Unbalanced moment is minus. Okay. Next, how do you get this? Minus 7.93 into 0.25.
Minus 1.989.
Is it minus or plus?
Plus, sir.
Plus, because unbalanced moment is minus. So balancing moment will be plus.
Plus, sir.
Okay, I think this first step is clear. Carry over. AD to DA it should go, but DA is not there in our list because we are considering only 50%. Leave it. Next, AB, where it should go?
BA.
BA, it is there in our list. Transfer it. Minus 3.3 divided by 2. It comes to minus 1.65. Okay? Is it correct or not?
Yes, sir.
Next, BA, where it should go?
AB, sir.
It is there. So
EB.
5.95 divided by 2.
2.975.
975. Next, this is there. BC, where it should go actually,
CB.
but it is not there in our list. So you leave it. Next case balancing, you have to see these two columns because A has got two members. This is no moment has transferred here means it is 0. So plus 2.95 plus 0. It is an unbalanced moment. So balancing moment will be how much?
Minus 2.9.
Very good. Minus 2.975. Do these contributions. Minus 2.975 into 0.25. Yes. Quickly.
Minus 0.744.
Yeah, minus 0.744. That's what I have written. Next, minus 2.975 into 0.75 because distribution factor of AB is 0.75.
Minus 2.1.
2.23.
Minus 2.23.
Okay. Yeah, even if you write 3 digit, nothing wrong in that. Write it, whatever you get, no problem. Next, you come to the B joint. What is the balancing moment at B joint? Balancing moment I'm asking.
Plus 1.6.
Yes, plus 1 point because unbalanced moment is minus 1.65. This is 0. If you add this, minus 1.6 will be the unbalanced. So balancing will be plus. Tell me now what is the contribution for a BA? Plus 1.65 into 0.75.
Plus 1.23.
1.2.
Yeah, 1.238. 4.
1.237.
Okay, no problem. You can write that. Next, for this, minus 1. Sorry, plus 1.65 into 0.25.
0.4.
0.4. Okay, you write that. Whatever you are getting, you write it at the end. The same. There will be no much difference in the decimals. Okay. Okay. Once, then carry over. See now, once if you put here arrows, now only those two will be carried over in the second step also. Here to here to here by 50%. Minus 2.23 divided by 2. Is it minus 1.115?
Minus 1.11.
Okay, then this 1.238 divided by 2, this, it comes here.
0.619.
Okay, whatever you get, you write 0.619. That's all. Now, again, you have to repeat that balancing and carry over. Balancing means it is now plus, so it will be minus. Minus 0.619 into 0.25 comes here. Check it. Quickly you do it. Minus 0.619 into 0.25. Yes.
Minus 0.15.
Okay, you went here. Next, this value. Again, minus 0.619 into 0.75. The distribution factor of AB is 0.75.
Minus 0.464.
Okay, then it is right. Come to this joint. See, this plus this is the unbalanced moment. So this is 0. Minus 0.115 is the unbalanced moment. Balancing moment will be plus. Plus 0.115 into 0.75. Yes.
0.086.
0.0865. Next, calculate the for BC. Plus 0.115 into 0.25. See, all,
0.028.
yeah, 0.02 something. Okay, right. See, all of you do it because unless you practice, you never get this idea. Only by practice only you can become perfect. Okay. Then carry over. Half of this will carry over here. Half of this will carry over here. This is 232. I think this is 232. It is. Then this is 043. If you get it. Okay. Then balance again. One more balance. If you do, you will get these values. Carry over, actually last cycle I said carry over with extreme end. But here it's a total closed structure, no extreme end is there. So I have stopped after balance. Okay. You add these moments, you will get the final moments. That is 3.99. It is minus 3.99. This is 6.52. This will become minus 6.52. You may get small differences in your calculation once if you change the difference. This may be 3.98 something or like that. But no problem. We'll get this plus this minus same. Okay. Okay, I think, shall I proceed further part? Now this is the bending moment diagram. Now, so far you have studied the portal frames with symmetry. Now we'll consider the portal frames with side sway. Now sway analysis, that is. Now first step. So as usual here, calculate the fixed moments due to external loading and carry out moment distribution. This first step remains same. Calculation of fixed moments. That means to carry out moment distribution, you need to calculate distribution factors also. That is step number 1, 2, 3. First, same. Calculation of fixed end moments, calculation of distribution factors. Third is moment distribution. This is due to external loading. It is called as a non-sway analysis. Okay. Next. Now to check whether there is a sway or not, calculate the horizontal reactions at the column basis. What you have to do after getting the end moments and the loading end moments, you have to calculate the horizontal reactions at the column basis. Right? The algebraic sum of the horizontal reactions will give the restraining force or holding force. I will show with an example afterwards. That means, so that net force on the frame will not be 0. If net force is 0, it will not undergo swing. So there will be some plus or minus force will come on the frame. And that force, horizontal force, will make the frame to swing. Right? That means algebraic sum of the horizontal reaction will be the restraining force. That is called as a holding force. The sway force S will then be opposite direction of the holding force. I will explain it when I solve the problem. Third step. Remove the holding force P and permit the joints to swing. So means that P is nothing but force required to keep it in equilibrium. So you will calculate what is the force required to keep it in equilibrium. But I don't want it equilibrium. That means that force is there in the opposite direction of the P. So that itself is called as a swing. Means you have to allow it to sway, then calculate the, means what I said, remove the holding force and permit, means if you remove that force which is required to keep it in equilibrium, automatically joints get swayed. And this will cause the set of arbitrary fixed end moments and then carry out the distribution of these moments. Means allow it to sway. So you have to assume some arbitrary fixed moments here. How to assume that? Again, I will come with different with problem and tell you that. Next, last one is calculate the horizontal reaction due to assumed arbitrary moments. Algebraic sum of the horizontal reaction of the column basis must be equal to the sway force. Calculated in step 2. If not, reduce the assumed sway moments proportionately. This, if you read, you will not understand. Along with problem, I will explain this. Okay. Last one, actual sway moments is equals to correction factor multiplied by assumed sway moments. All these will be, I am going to explain you in the problem. Before going to the problem, just I will give you how that I have told assumed or arbitrary moments. How to assume those arbitrary moments? Listen to this. Ratio of sway moments at column heads. Column head means it is here it is BA. This column is say CD. This BA is column head of AB member. CD is column head of CD member. Okay. Okay. Listen here. When the joint sways, a set of moments at the column heads and bases are introduced. The ratio of the sway moments at the two column heads will depend upon the end conditions of the column. Okay, we'll see what is that. Now, expression for column head moments. First case I will take when both ends of the columns are fixed. Say this is A is fixed, D is fixed. Okay. Now, if you allow it to sway, you know that it sways like this. Okay. This is the amount of sway at B. This is the amount of sway at C. Of course, both will be same. Now, as the ends are fixed, so that slope will be 0 here, slope will be 0 here, okay, as well as the deflections. Let I1 be the moment of inertia of the column BA, L1 be the length of the BA. Similarly, here, I2 be the moment of inertia of the column CD, and L2 be the length of the CD. I am concerned with columns because the columns getting swayed here. I am not talking of beam now. When it is lateral movement takes place, beam goes along with the same line. Okay. Now, so you to deflect like this, what is the kind of moment required at end B now for this column? To bring this B to this position, What is the nature of moment required at B? Can anybody tell me? Say I want to bring this to this side. Then what is the moment required? What is the nature of moment required? Clockwise or anti-clockwise? Yes, anybody? What is the nature of moment at required B such that B should come to this position? Say B dash. Anybody? You have to bring it right. Suppose if you keep AB horizontal, if you want to bring it down, what is the end moment required at B to bring it down? Assume that AB is vertical now. You bring it to the horizontal. A left, B right. Anybody? Hello? Are you listening or not first? Hello? Hello?
Yes, sir.
What is the nature of moment required to bring from here to here? You have to push that column towards right. Then what is the nature of moment required to push it towards right?
Anti-clockwise.
Anti-clockwise. Very good. Because this you have to bring it and you have to do like this. This is a anti-clockwise. And similarly here also this is anti-clockwise. Right? Now, if you take the ratio of that MBA divided by MCD, ratio of column head moments, not same column end moments. BA, MBA divided by MCD. This is called a ratio of column head moments. What is the moment required to bring it or settle down by delta? You already derived it in your slope deflection method. I think it is 6 EI delta by L square. Do you remember that? The moment required to settle anything by delta, it is moment required is 6 EI delta by L square if the far end is fixed. So means it is 6 EI delta by L square of this, means 6 EI. 1, I is I1, L is L1, L1 square into delta. Similarly, for this column, there is also 6 EI delta by L square, but I is I2, L is L2. If you simplify this, what you will get? So 6 EI, 6E cancels. Delta, delta cancels. You will be left with I1 by L1 square, I2 by L2 square. Right? You have to get the column at moments in this image. You have to enter the I of the column AB, enter the length of the column, square it. Then in the denominator, enter the I of the column CD divided by length square of that column. Whatever number you will get, you have to assume those numbers as the column head moments. Next, when both columns are hinged. Okay. Now, again here the moments are required is anti-clockwise only. But what is the moment required at the end to cause settlement delta if the far end is hinged? Far end is fixed, you know that it is 6 EI delta by L square. What about if the far end is hinged? I think it is told again during the derivation of slope deflection equation. Please go through it. It is a 3 EI delta by L square. If the far end is fixed, the moment required to cause settlement is 6 EI delta by L square. If the far end is hinged, it is 3 EI delta by L square. Okay. Therefore, again, this end is also hinged. This end is also hinged. It is 3 EI by delta by L square. I is I1. Delta remains same. L1 square. It is I2 by L2 square. Again, entering 3E delta common, they will cancel. So therefore, you will be getting with MBA by MCD is equals to I1 by L1 square, I2 by L2 square. This ratio will not change if both ends are fixed or both ends are hinged. Same. That means you have to calculate MBA by MCD is equals to I1 by L1 square divided by I2 by L2 square. Third end condition, when one end fixed and other end hinged. Look at this. This is fixed, this is hinged. Now, can you tell me what is the moment required here at the end B for the column AB? What is the moment required to cause the settlement delta at the end B of the column AB when the far end is fixed? Quickly, can you tell me? Hello? It is 6 EI, just now I have told. It is 6 EI delta by L square. What about this? Now this far end is hinged. 3 EI delta by L square. Now if I write the column head moments ratio, MBA by MBD, sorry, CD, MBA 6 EI delta by L square, MCD is 3 EI delta by L square. Of course, you enter I1 and L1 for the AB member and CD, I2 and L2. Now what will be the ratio? Can you tell me now? Here 6 EI delta, 6, sorry, E delta is common. Okay. So it will become 2I1 by L1 square divided by I2 by L2 square, isn't it? Because it is 6 and 3. Earlier, I1 by L1 square divided by I2 by L2 square. Now it is, this is 6, this is 3. So it will be 6 by 3, means it will be here 3 into 2, it will be 2. 2I1 by L1 square, it is only I2 by L2 square because E cancels, delta cancels. Is this clear? Suppose if this is hinged and this is fixed, anybody tell me? Suppose assume that A is hinged, D is fixed. If A is hinged, D is fixed, then what will be the column head moments, ratio of column head moments? Anybody? Now I have taken A fixed.
I1 by L1 square by 2 I2 by L2 square.
Very fantastic. Because now if A is hinged, if the far end is hinged, this will become 3 EI delta by L square. And if this is fixed, far end is fixed, so this will become 6 EI delta by L square. It will get reverse. That is, MBA will be 3 EI delta by L square. It will be 6 EI delta by L square. And if you simplify that, therefore, you will get here I1 by L1 square, that divided by 2I2 by L2 square. Is it clear? Hello?